Hey everybody, this is going to be chapter 3, describing data numerical measures. So admittedly, this is a pretty cool chapter. You get to learn about things like mean, median, mode, standard deviation, and variance. But these are things that you will probably be using for quite some time if you do anything analytical for a job. These things are a little bit scary to some people, but I think having an intuitive grasp of it is really, really important and really helpful for looking at data and understanding it, and frankly, the rest of the class. So this chapter is going to have 6 learning objectives, though I'm not sure I have all of these in the slides. I think I've taken some of them out. But this is supposed to be a 2-day lecture, so I'm going to make 2 videos. I think it would be helpful to watch the first one, digest it, and then watch the second one, and so on. So I'm going to really be focusing on these first 2 learning objectives to start. So we're going to be talking about measures of location. So we talked about frequency distributions last time. So you make these distributions, they look great. You have a histogram, or you have some sort of frequency polygon, or whatever those crazy things are. And your boss is asking you like, oh, help me understand the distribution of the age of our patrons, whatever. So, you are a credit card company, and you want to know what the average age is. You want to know what that looks like, what that distribution looks like. Well, you can't really print out like a distribution and just show people that. You need ways to summarize your data. You need measures of central tendency, measures of dispersion, things like this. So the first step is you have some sort of distribution, you have some sort of data set. Where's the middle? What's the middle point, right? That's what a lot of statisticians and mathematicians have been trying to figure out for a very long time, and we've come up with 3 main measures. 2 of them are very intuitive, and one of them is probably the one that you use the most often, the mean or the average, though it's probably a little bit less intuitive. So for example, we have mean, median, and mode. So mean is, again, just the average. You take the sum of all of your data, all of your observations, and then you divide by the total number of them. The median is literally ordering the data and splitting it right down the middle, and wherever that middle is, that's the middle of your data set. And then finally, the mode. The mode is the observation that occurs most frequently. So there's 3 different ways you can kind of think about this. Many of them have different interpretations and implications. But this last bullet point says that the arithmetic mean is the most widely reported measure of location. There are different types of means, like the geometric mean and the harmonic mean, but we won't be talking about those. Okay, so if you remember from the first class, we have populations and we have samples. So this is a little bit annoying of a point here, but it's really important when we start talking about hypothesis testing halfway through the class and then forever on in statistics. So a population mean is denoted by this little Greek letter called mu. Looks like an M or a U, but it's pronounced mu. So this sigma right here, this Greek letter sigma, is what you put next to some sort of letter or variable when you want to sum it up, when you want to add all of these things up. And X is your data, right? So if you have ages, you're going to add up all the ages. That's what sigma X is telling you. And then divide by N. So capital N is your population size. So this is an important distinction because later we'll use lowercase n. But mu is the population mean. Sigma X is the sum of all the X's. And capital N is the population size. So this is a measurable characteristic of a population, and we call these things parameters. So these are like population parameters. Like these are like truth. Like the population average height of people in Econ 225. I can take all of your heights, add them up, divide by n. That's like the population parameter, right? Now there's also, this is a little bit out of order, but I'll talk about sample mean and I'll go back in a moment. So sample mean is if, let's just suppose I take the left half of the class. I pull them out and I say, okay, there are only 100 of you. That's going to be my little n. So lowercase n is going to be my sample size, sum of the x of that smaller sample. And then x bar is going to be my sample mean. So this is going to be the characteristic of a sample. Now, if I just grab half the class and take the average, is that average going to equal the population average? Almost certainly not, right? It'd be very surprising if I took a random sample and those two things were equivalent. Now, later in class, we'll be able to do some sort of high-powered statistics or low-level statistics maybe, and look to see if, okay, how far is this thing really? And is my sample that far off where it doesn't even look like it came from this population, right? So we'll be able to test those things later on. But let me go back a little bit to population mean. So here's an example. There are 42 exits on I-75. Here the distance between the exits in miles. So the question is, why is this information a population? The answer to this question would be that, well, these are all of the exits on I-75 through Kentucky, right? So there's not like we only looked at the even ones or we only looked at the first half, right? These are all of them. And what is the mean number of miles between exits? Not going to do the math, but you would just add them all up and divide by 42. So again, 192 divided by 42 equals 4.57. The sample mean we just talked about. Again, it's just going to be adding up. That's what sigma means. Add all the x's and divide by n. I know I'm being a little bit slow with this, but when we start doing a little bit more complicated things and there's sigmas in there, I want you to be able to remember that, oh, all that means is sum. Okay, so Verizon is studying the number of minutes used by clients in a particular cell phone rate plan. A random sample of 12 clients showed the following number of minutes used last month. So 90, 91, 77, 110, blah, blah, blah. What is the arithmetic mean? Number of minutes used. So arithmetic, if you see that, it just means like regular average. It's just like a fancy word to denote it from other types of averages, like I was saying before, the geometric and the harmonic. But the sample mean is calculated the same exact way. There is no difference. You just add up all the numbers you have and divide by however many you have. This is not the case for variance, which we'll talk about in the next video. Okay, so let's talk about the properties of arithmetic mean. You need an interval or ratio scale of measurement. It wouldn't make sense to take, like, for example, we talked about top party schools in the country. And we talked about WVU, ASU, Tulane, and Wisconsin, I believe. So those were the top 4 party schools. It wouldn't really make sense to take an average of those because, like we were saying, we don't really know how much more of a party school 1 is versus school B, school 2 versus school 3, whatever. So we need to, it's very particular that you need to have like some sort of continuous or interval data. All the data values must be used in the calculation. This is obvious because you're summing them all up. It's unique. In other words, that each data set has one single mean. You can't have 2 averages. That doesn't make sense. The sum of the deviations from the mean equals 0. So this is a little bit tricky of a point, but let me just explain it with a really simple data set. Imagine the numbers 1, 2, and 3. If you add these all up, 1 plus 2 is 3, plus 3 is 6. Divide by 3, your average is 2. The sum of the deviations meaning 2 minus 1, right? That's going to be 1. 2 minus 2 is 0. And 2 minus 3 is -1. If we add those up, 1, 0, and -1, you get 0. This is true for every single average you ever take. So if you ever take some average minus all the values and whatever those numbers are, and you add up all those, the results of all those numbers, you'll always get 0 no matter what, unless you're doing some sort of rounding, but you'll always get 0. And then finally, a weakness of the mean is that it is affected by extreme values. So just as an example, UNC in the 80s or something like this had the geography major or geology major, something like this, and they were trying to calculate what their average student income was post-graduation. So they had all their data and they added it all up, divided by n, and they said, hey, our average graduate makes, I'm making this up, but $200,000 after graduation on average. And people were looking at that, say, like, that sounds really strange. Why is it like that? And the answer was that Michael Jordan went to UNC and was a geography major or whatever. And because his salary was like $30 million, it brought up the average so much that it made everyone else look kind of ridiculous. So these extreme values, or outliers, as we call them in statistics, can really affect the mean. The mean is really susceptible to being skewed or being drawn out by an outlier. And it can all of a sudden no longer represent the middle, right? It's only middle if the distribution is somewhat symmetrical, which we'll see in a moment. Okay, the median. So the median is just ordering the points and finding the middle. So for example, here the price is ordered from minimum to maximum and then maximum to minimum. If we order these data sets, the middle is always going to be the same. There's 5 data points here, which is really handy because if you're trying to figure out the middle, it's always going to be a unique value. Now, if we have an extra value, right, if we have 6 values, what you have to do, so like suppose we added like 1 million here, you would have to find the average, the arithmetic mean of 70 and 80. So the median, if there were 6 values and it was much higher, would be $75,000. So characteristics of the median. The median is the value in the middle of a set of ordered data. At least the ordinal scale of measurement is required. So for example, you can find the median party school, I guess. Again, because you can find that middle point, like this is the middle one, but it still doesn't really tell you that much information if it's ordinal. You really want to have that ratio or interval measurement to really kind of understand median and central tendencies. 50% of observations are going to be larger than the median. Now, they could be much larger than the median. In the Michael Jordan example, he is way larger than the median value. But in this case, the median value in the Michael Jordan case is likely much more representative of the middle of the distribution, where he was just one outlier. And then again, each data set is going to have only one median. It doesn't make sense to have 2 middles, right? In the case where there's an even number of observations, you have to take the 2 middle ones and then you find the average of those 2, and that is the median. To find the median, you want to, so this is just kind of talking about that if there's an even data. So you're going to sort the data, there's an even number. So the way I would do this, if I were you, is I would just like cross off this one, cross off the 17, cross off the 3, cross off the 10, and just keep going in until you can find the middle. That's the easiest way to do it. And then the median is 6 because the middle is really between these 2 numbers. So the average between 5 and 7 is 6. Okay, the mode. The mode is the value or the observation that occurs most frequently. So this is going to be just, if, for example, you gather a data set of people, the modal income is probably going to be 0 because everyone makes a little bit different dollar value, right? Whereas there's a clumping of people at zero. So there's some sort of, so does that describe the distribution of income? Probably not. But I digress. So characteristics of the mode could be found for nominal level data. So for example, if you have data where it's just names like number of, I'm not sure what this, bath oil or something, more a soothing, smell nice, far out, whatever, you just pick the one that's the most. This is okay for ordinal data, even though if there's an ordinal, there really shouldn't be multiple on the same data or the same value. Interval ratio, you can just find the most frequent every time. And then this point here, a set of data can have more than one mode. So you can't have more than one mean. You can't have more than one median, but you can have more than one mode. So for example, if you have 10 people with who make $10 an hour and however many, the same number of people that make $100 an hour, you'll have the same mode for these two people or for this group of data. Okay. So relative positions of the mean, median, and mode. So we're going to talk about bell curves, which is what these are, a little bit later. But let's suppose you have a distribution of age, and here's the frequency, right? So in this case, we have a symmetric distribution where the mean, the median, and the mode are all equivalent. This is like a dream case. This never really happens in real life, but this is the case where the average, the median, and the mode are all telling you the same thing. So in this case, you can probably trust that your data are symmetrical. In the next one, in the middle one here, we have positively skewed distribution. This would be the case of like Michael Jordan, right? So you have the normal distribution, and then you have this guy way out here who's making way too much money, bringing the mean really, really high. Now the median is, again, pretty much in the middle, like it must be by necessity. And then the mode is even more to the left of this. So if you notice some sort of ordering like this, you know you have something called positive skew. Similarly, if the mean is much lower than the median in mode, then you're going to have something called negative skew. Again, this is only for like single hump data. If there's multiple humps, like maybe there's a hump here, and then there's a hump here, and they're the same height, you might have two modes, right? And the median could actually be right in the middle of those two, or it could be on either side. So there's all sorts of, little quirks that might arise. But this would be a case of negative skew, meaning that you have the opposite case of Michael Jordan. You have a bunch of basketball players who are making a ton of money, and you have like a couple of geology students who are making like not so much. Okay, this is going to be the last slide. It's called the weighted mean. So you're going to see this formula and you're going to like freak out, but it's really not that crazy. All it's doing is making your life easier. Suppose you have a data set of 180 observations or something like this, but you have but these data repeat over and over again. For example, you have 10 people that make $10 an hour, and you have 20 people that make $5 an hour. To find the mean of this, you can add up 10 plus 10 plus 10 10 times, and then you can add up 5 20 times, and then divide by 30. Or what you can do is you can just say, I know that there are 10 people who make $10 an hour. So I could just do 10 times 10, it's 100, plus 20, right? 20 people that make $5 an hour. So that's another 100. And then I can just divide this by 30. So I have Excel open on my other screen here, but 200 divided by 30 means that the average wage per hour is $6.67. So this is a really easy way to calculate the mean instead of having to do this huge, long calculation, right? That's all this is saying. So if you see some sort of question that looks like this, the Carter Construction Company pays its hourly employees $16.50, $19, or $25 per hour. There are 26 employees. 14 are paid 16.50. So this is going to be 14 times 16.50. 10 at 19, so 10 times 19, and 2 times 25. So exactly what this is doing here. And you can see how this calculation is much shorter instead of having to write the 26 numbers next to each other, right? So this is a much easier formula to do. So weighted mean, if you see something like this, it really is simplifying your calculation a lot. Okay, so this next one is dispersion. We're gonna save that for next class. But I have here some example data here. So I'm just gonna go over this really, really quickly. But suppose this was our data set like this. If I wanted to find the average of this, well, in Excel, there's some functions we can use. But essentially what I'm gonna do is I'm just gonna add these all up. So I'm just gonna use sum, add these guys all up, get 28 divided by, and I can use this function called count. And it's going to count the number of values that are here. I already know it's 9. I can see it, right? But if this was a really much larger data set, you'd have to, you wouldn't be able to count maybe. So the average is 3.11111 for this data set here. The mode, if we look at it, is going to be 2, because 2 occurs 3 times. 4 and 5 occur only 2 times. So 2 is the mode. So maybe I'll write it down this way. You say mean mode is 2, and the median is going to be 1, 2, 3, 4, and 1, 2, 3, 4. The median is going to be 3. So if we see this, right, if we go back to our previous plot here, if we see this sort of thing where the mean is the largest, the mode is the smallest, and the median is the middle one, then we're going to have this thing called positive skew. So if the mean is bigger than the median, or the mean is bigger than the mode, you know that this is going to be positive skew. Now I have this other data set here, which is essentially the same thing, just took off this 5. The median becomes a little bit more difficult to calculate because there's 8. But we know that we just take the average of the middle 2 values. So this would be 2.5. But anyway, this next point here is going to be why study dispersion, which we'll talk about in the next video.